Section 9.2 of your textbook describes the method of solving quadratic equations by completing the square. Completing the square is a process in which a constant is added to a binomial in order to obtain an expression that is a perfect square trinomial. Let's first see some examples of how to complete the square, and then we'll look at how this process can be applied to solving quadratic equations. Our first binomial is x squared plus 8x, and we want to add a constant in order to create a perfect square trinomial. Remember that a perfect square trinomial has the form a squared plus 2ab plus b squared. Therefore, when we look at our binomial x squared plus 8x, if we look at the first term, we can see that a squared is equivalent to x squared, and thus a is equal to x. Moving to the second term, since a is equal to x, we know that 2b is equal to 8. Therefore, b is 8 divided by 2, or 4. Thus, the constant we need to add to create our perfect square trinomial is 4 squared, or 16. X squared plus 8x plus 16 is a perfect square trinomial. It's the square of the binomial x plus 4. Moving to our second example, once again we can conclude from the first term that a is equivalent to x, and then from the second term that 2b must be equivalent to negative 10. This means b is negative 5, and therefore b squared is 25. So we write the perfect square trinomial x squared minus 10x plus 25, which is the square of the binomial x minus 5. Moving to example number 3, we can see the same pattern developing, and we notice that since 2b is equal to 5, the coefficient of our second term, b itself must be that coefficient divided by 2, and then b squared would be 5 over 2 squared. This means our perfect square trinomial is x squared plus 5x plus 25 over 4. And then in our fourth example, we can generalize this process a little bit to see that in any expression of the form x squared plus bx, to complete the square, we simply need to take half of our coefficient of x, so in this case that would be b over 2, and then square it. This gives us the perfect square trinomial, x squared plus bx plus b squared over 4. Now, why is this process of completing the square useful? Well, it can be used to write an equivalent quadratic equation that can be solved using the principle of square roots. Let's describe the process and then look at several examples. To solve any quadratic equation by completing the square, we'll use 4 steps. First, if a, the coefficient of x squared, is not equal to 1, we will divide both sides of the equation by it. Second, we'll subtract the constant term from both sides of the equation. Third, we will complete the square, adding the square of half of the x coefficient to both sides. And then finally, we will factor and use the principle of square roots to solve our quadratic equation. In all the examples that follow, we're going to be solving the equations over the set of real numbers. So we will include only real numbers in our solution sets and not imaginary numbers. Problem number 1, we have the quadratic equation x squared minus 4x minus 2 equals 0. In this case, our coefficient of x squared is 1, so we can skip that first step and move right on to eliminating the constant term from the left-hand side. We'll do that by adding 2 to both sides of the equation. So we have x squared minus 4x equals 2. Now on the left-hand side we have a binomial. We'll complete the square of that binomial. Take half of the coefficient, negative 4, which is negative 2. Then we square it, so we have 4, and we will add that on both sides of the equation. Now we can factor the left-hand side, since it's a perfect square trinomial. It's the square of the binomial x minus 2. And on the right-hand side, we have 6. Now, since the left-hand side of our equation is a perfect square, we can use the principle of square roots to solve. Taking the square root of both sides, we obtain x minus 2 equals positive or negative the square root of 6. Then adding 2 on both sides, we see that x is equal to 2 plus or minus the square root of 6. This means we have two irrational numbers as solutions of our quadratic equation, and they are 2 plus the square root of 6 and 2 minus the square root of 6. Let's move to our second example. X squared plus 6x plus 13 equals 0. Once again, our coefficient of x squared is 1, so we'll move right on to step 2 and subtract 13 from both sides. So we have x squared plus 6x equals negative 13. To complete the square on the left-hand side, we need to take half of 6, which is 3, and then square it. So we will add 9 to both sides of our equation. Factoring the left-hand side, we have the quantity x plus 3 squared. Simplifying the right-hand side, we have negative 4. Using the principle of square roots, we would have x plus 3 equals plus or minus the square root of negative 4. In this case, we see that the right-hand side is the square root of negative 4, which is an imaginary number. Therefore, there are no real solutions for this quadratic equation, and so we'll write our solution set as the empty set. Let's do two more examples. In these two problems, a is no longer equal to 1, so we'll need to use that first step of our process. In problem 3, we have 3x squared plus 15x minus 24 equals 0. So we first need to divide both sides of the equation by 3. And on the left-hand side, remember that means we'll divide each term by 3. So we have the equation x squared plus 5x minus 8 equals 0. Now we add 8 to both sides and complete the square on the left-hand side. Take half of our x coefficient and square it, and add that number, 25 over 4, to both sides. Factoring the left-hand side as the square of a binomial, we have x plus 5 over 2, that quantity squared. On the right-hand side, in order to add 8 plus 25 over 4, it would be helpful to write 8 as 32 over 4 so that we have a common denominator. Now we can use the principle of square roots. Take the square root of both sides of the equation. We have x plus 5 over 2 equals plus or minus the square root of 57 over 4. And simplifying the square root of 4, we have plus or minus the square root of 57 over 2. Now subtracting 5 over 2 from both sides, we have x equals negative 5 over 2 plus or minus the square root of 57 over 2. Since we have a common denominator, we could also combine these two terms and write the quantity negative 5 plus or minus the square root of 57 all over 2. Either way of expressing those solutions would be acceptable. So in our solution set, we can write the following two irrational numbers. Negative 5 over 2 plus the square root of 57 over 2, and negative 5 over 2 minus the square root of 57 over 2. Let's do one final example. The equation 2x squared minus 7x plus 6 equals 0. First, we need to divide both sides of the equation by 2. Then we need to subtract 3 on both sides. Now we complete the square. Take half of our x coefficient. Well, since our x coefficient is negative 7 over 2, half of that would be negative 7 over 4. And then we square that. So we would have 49 over 16. We add that number to both sides. Factoring the left-hand side, we have the quantity x minus 7 over 4 squared. On the right-hand side, let's get a common denominator. Negative 3 would be equivalent to negative 48 over 16. but we're adding 49 over 16. So the right-hand side simplifies to 1 over 16. Take the square root of both sides. And since the square root of 1 over 16 would be 1/4, we have plus or minus 1/4 on the right-hand side. Finally, we can add 7/4 to both sides. And then in this case, we can simplify our answers by first taking 7/4 plus 1/4, which is 8/4, or 2. That's our first solution. And then we can take 7/4 minus 1/4 and get 6/4, or 3 over 2, as our second solution. So our solution set has two numbers, both rational numbers in this case, 3 over 2 and 2.